Module 6. Circles with Angles. Definitions and radian measure. In Module 2, we defined a circle to be a collection of points equidistant from a fixed point, called the center. A line segment from the center to any point on the circle was called a radius, while a line segment that connects two points on the circle and passes through the center is called a diameter. An arc is a piece of a circle, while a chord is a line segment that connects between 2 points on the circle. So the diameter is really a special type of chord that passes through the center. It is clear that if the radius of a circle is r and d is its diameter, then d equals 2r. The diameter is twice the radius. As we said before, a fundamental property of a circle is that the ratio of the circumference to a diameter, or c over d, is the same quantity for any circle. This ratio, or this number, is called pi, and it's about 3.14 in numerical value. In Module 1, we discussed that angles can be viewed as a portion of a circle, where a full revolution is 360 degrees. Sometimes it's convenient to use a different angle system. The radian angle measure is defined to be 2 pi radians in a full revolution. Thus, a half revolution, that is a straight angle, is 1/2 of a full revolution, or 2 pi radians. So we see that 180 degrees equals pi radians. This gives us an easy method of converting radian measure into degree measure. If an angle is pi over 12 radians, to convert to degrees, we simply can replace pi by 180 degrees to get 180 divided by 12, which is 15 degrees. Thus, pi over 12 radians measures 15 degrees. To go from degrees to radians is a bit more tricky. We can observe that as pi radians is 180 degrees, it follows that pi divided by 180 radians is 1 degree. For example, suppose that we want to convert 40 degrees into radians. We can say that 1 degree equals pi over 180 radians, and so 40 degrees equals 40 pi over 180, which is the same as 2 over 9 times pi radians. The reason why radians are useful is because they simplify the area formula for sectors that we discussed back in Module 2. Recall that if a circle has a radius r and a central angle of theta degrees, the sector of the area is given by theta over 360 times the overall area formula, or pi r squared. Suppose that theta is measured in terms of radians instead of degrees. As pi radians equals 180 degrees, we can say that 1 radian equals 180 divided by pi degrees. Thus, if an angle is theta radians, it will then be 180 divided by pi times theta degrees. Putting this into the sector area formula, we can use a little algebraic manipulation to get the formula that the area of a sector is 1/2 of theta times r squared. Consider this sector example. For this example, we'll say the sector angle is measured in terms of radians and given us as pi over 6, and the radius is 4 units. Using the formula, the area of the sector is 1/2 times pi over 6 times 4 squared, and when you multiply it out, you get 4/3 pi. Another nice feature of using radians instead of degrees is that they allow us to more easily compute arc lengths. Suppose we're given an arc with an angle theta measured in degrees. Since theta divided by 360 is the fraction of the arc of the full circle, and 2 pi r is the full circumference of a circle, we get that the fraction of the length in this arc is theta divided by 360 times 2 pi r. With a little algebraic manipulation, it comes out to theta divided by 180 times pi times r. This formula is not exactly nice looking, but notice what happens when we measure the angle in radians. Instead of theta, we give it in radians. Since 2 pi is a full revolution, we have theta divided by 2 pi as the fractional part of the arc of the total circumference. Thus, its arc length is given by theta divided by 2 pi times 2 pi r, which is the same as theta times 2 pi divided by 2 pi times the radius, and when you cancel out the 2 pi's, you get theta times r. All we have to do is multiply the radian central angle by the radius to get the arc length. Inscribed angles. We can describe a circular arc by its central angle measure. Thus, even though circular arcs are quantities of length, we can find it convenient to describe their size by the angle of the central angle that they produce. When we say a circular arc is 30 degrees, what we mean is that the arc produces a central angle of 30 degrees. Radians, which we just discussed, are useful for computing the actual lengths of the arc and the area of the sectors, but if we only want to describe a circular arc without caring about its length, then we might as well use degree units. An inscribed angle is an angle produced by two intersecting chords on a circle. We say that the inscribed angle is inscribed, in this case, by arc AB. The inscribed angle theorem says that the inscribed angle is 1/2 of the angle measurement of the arc. For example, in our case, if arc AB is 50 degrees, that will mean that the inscribed angle is 25 degrees. There are multiple important consequences of this theorem. The first is that inscribed angles of the same arc are equal. Notice in this picture that the three inscribed angles are all inscribed by the same arc. Thus, they're all equal angles. The second consequence is known as Thales' theorem. It says that an inscribed angle by a semicircle is a right angle. It's clear that a semicircular arc measures 180 degrees, and so the inscribed angle, being half of that, is 90 degrees. Angles between chords. Suppose that two chords intersect, not on the circle, which is an inscribed angle, but somewhere inside the circle. We can find the angle they produce by the arcs they generate. From the picture, the inscribed angle theorem, we have that angle CBA is 1/2 of the arc of AC, and angle BCD is 1/2 of the arc BD. Now, since angle CEB plus theta in this diagram equals 180 degrees, because they're adjacent intersecting angles, and angle CEB plus CBA plus BCD equals 180 degrees because of the sum of all of the angles in a triangle, it follows that theta is angle CBA plus angle BCD. Therefore, theta is angle CBA plus BCD, which is the same as 1/2 of the arc of AC plus 1/2 of the arc of BD, which means overall we get that the theta is 1/2 of arc AC plus arc BD. Thus, the angle between two chords is the average of the arcs that they generate. Tangents and secants. A tangent line to a circle is a line that touches the circle at only one point, whereas a secant line is a line that passes through 2 points. There are 3 cases of angles formed between tangents and secant lines. The first case is when 2 tangents intersect at an angle. The second case is when 2 secants intersect at an angle. The third case is when a tangent and a secant intersect at an angle. In each of these 3 cases, the angle of the line is given by half of the difference between the outer arc and the smaller arc. That is to say, in this diagram, is that theta equals the blue arc minus the red arc divided by 2. Cyclic quadrilaterals. A quadrilateral, which is a 4-sided figure, is called cyclic if it can be put on a circle. The main result about angles of cyclic quadrilaterals is that their opposite angles always add up to a straight angle. To see this, note in this case that angle ABC is 1/2 of the arc of ADC, and angle ADC is 1/2 of the arc of ABC. Therefore, angle ABC plus angle ADC equals 1/2 of arc ADC plus 1/2 of arc ABC, which is the same as 1/2 of 360, which is 180. Here we use the fact that these 2 arcs together are a full circle, which means that their measures have to equal 360 degrees. For example, this quadrilateral is not cyclic, since its opposite angles do not add up to 180 degrees.